Now, to properly understand the model, let us start with a forward pass based weight calculation. So, first of all, we will calculate the weight of all these neurons from input layer to hidden layer. So, these weight calculations are very simple. This is like input x1 into the weight of neurons w1 to h1. Similarly, second weight is w21 to h1 into x2 w312 means this is w31, this node weight into x3 and so on. That's why we can, by using same way, we can calculate the weight of h1. Similarly, we can calculate the weight of h2 and h3. So this is the process to calculate the weight of h1, h2 and h3. We can represent these all weights of h1, h2 and h3 in a form of matrix like that. So you can see that we can easily exchange each other. As we discussed earlier, that hidden layer doesn't contain the activation part. So all the summations of product of input and neuron weight will act as a weight of the node of the hidden layer. So we will pass this hidden layer weight to the next layer without calculation of such kind of activations that we generally calculate in the case of traditional neural network. So the next part of forward propagation is the weight calculations from hidden layer to output layer. Now here let us represent the weight of neurons from, as we discussed earlier, from h1 to w11 as a w-11 and h1 to and h2 to o11 as w-21, h3 to o11 as w-31. Now the summation part of this weight can be calculated by taking the weight of h1 into this neuron weight of h2, and from neuron weight from h2 to o1 weight of h3 and neuron weight from h3 to o1. So it will be just like a summation. We represent this weight as u11. Similarly, we can calculate the net or summation weight O12, summation weight for O12, summation weight for O13, summation weight for O14 and summation weight for O15 like this. And we can represent this as a simple matrix multiplication also. Now the next part of the weight forward pass at the output layer is the calculation of activation function, which is achieved by the softmax calculation. And in the softmax calculations, we use this summation weight obtained here with the help of these hidden layer input nodes and the weighted neurons that is calculated here. So the softmax output at O11 is nothing but exponential of net O11 divided by sum of exponential of all summation weights at all other nodes of the at the same context window. So you can see that out O11 or output weight of O11 and also represented as Y11 can be given as net O11. Here you can see the net O11 is the net input weight at this layer, and similarly net net O12 is the summation weight at this node. So we just take the exponential of each of these weights and represent this, which is equivalent to probabilistic score also, which is just a probability also, and we can also represent net O11 as U11, and this can be here written as U11 net e to the power net O11 as e to the power U11, e to the power net O12 as e to the power 12, and so on. Similarly, we can calculate the weight of output weight of O12 like this. Similarly, we can calculate the output values of output weight values for O13, O14, O15, which is represented as Y13, Y14, Y15. So these are the output weights like Y11, Y12, Y13, Y14, and finally Y15. Now after that we can calculate the error also. Now the next part is the error calculation. As we discussed earlier, that in this example for word model we are trying to identify the words which fits in the size of k word window and nearest to this word, semantically or logically related to this word. So in the probabilistic term we can say that in the current case we are just considering for 3 words. So let W1J, W2J, W3J. In this case W1J means jth word in the context C is equal to 1. W2J means jth word in the context C is equal to 2, and W3J means jth word in the context C is equal to 3. Here J is the just vocabulary, represents the vocabulary, and value of J is from 1 to 5. So it may be any word from, in this case W3J, it may be any word from W031 to O35. Because we discussed earlier, from the each context window we select a single word as an output. So now let W1J, W2J, W3J are the actual output words for the given single input word Wi, where W1J is the jth word of the first context window and J can be any number from 1 to 5. Now here the training objective is to maximize the conditional probability of observing the actual output word W1J, W2J and W3J for a given word Wi or a given input word Wi. We can also say that we want to minimize the error, so that loss function can be defined by conditional probability in terms of exponentials. So we take negative of conditional probability of occurrence of word W1J, W2J, W3J given the word input word Wi, which can be further simplified like this. So this is for the case of c is equal to 1, this is for the case of c is equal to 2, and this is for the case of c is equal to 3. So we can simplify this as a product of log of 3 different probabilities. We can also generalize the case by considering total C context window and a vocabulary of size j words. So we can say that error is negative of log of conditional probability of getting a word W1J, W2J up to WCJ given input word Wi, and this can be generalized here from c is equal to 1 to 3 because here we are using just 3 context windows 1, 2, 3, c is equal to 3. So in this case, if we take c is equal to capital C, then we can generalize it like this, and we can finally represent it in a simple way. We can convert this into a summation form by this part through j. So finally we can calculate the error by taking log c is equal to 1 to c, and this will be equivalent to this. Here we represent this j star to represent the actual output word in every context window. Now if we take the derivatives, actually in the main aim behind the error calculation is to apply some back propagation by using gradients. So let us start with some derivatives. So it starts with derivative with respect to UCI. When we take the derivatives, then it can be simplified. These derivatives are very simple. Just take the derivatives of dE, this part, with respect to UCJ. This will result in, this is very simple log based derivations. Log x is equal to 1 by x. So if in place of x, suppose we have some other variables attached with this, so then we can simplify like this part, and this part derivation of this part will be represented as this. So here YCJ is the out score of jth word in the cth context window, and JC1 equal to 1, JCJ is equal to 1 if the jth word in the cth context window is the actual output word. Otherwise we will take ZCJ as 0. So this is the initial derivation. So now we will start the back propagations. The major aim behind the back propagation is to update the weights of the neurons from hidden layer to output layer, and then from the input layer to hidden layer. In other words, we can say that we have to update this matrix, weight of this matrix. Now it is important to note that actually from the input layers, if we just see how the neurons weights are calculated, then you can see this, that the same matrix will represent all these weights for this context, and this context. So we will only consider updating the weight of this matrix, and after that we will use those weights and errors, calculated errors, and derivatives to update the weight of this matrix. And this matrix also represents the weight of neurons, attached neurons. As we discussed earlier, this represents W11, W12, H1. This represents W12, W12, H2, like that. So let us start with hidden layer to output layer. In this case, we update the weight of all neurons from hidden layer to output layer. So now taking the gradient to update the weight, we take the gradient with respect to W1 dash. As we discussed earlier in our previous tutorials, how backpropagation system works in with the deep neural network. You can just check the tutorials on deep neural network. Here I have discussed, I already discussed regarding the calculation steps for backpropagation. For example, to update the weight of this neuron from H1 to O11, we will just take the derivative of error at O11 with respect to W-11. So this is a general way to calculate the gradient. Now we can apply the chain rule, because the chain rule will work like that. Suppose we divide, I also discussed such kind of chain rules in deep neural networks related tutorials. So this is the output part, output activation part, and this is the net part. So we will use the chain rule from here to here. So we can break this like derivative of E011 to with respect to UC1 and derivative of UC1 with respect to W11. So first from out to net, so here we will replace like DE UC1 into, this is net part, and then UC1 to W11. So this is the traditional way of applying chaining rule in backpropagation. So this way, by using this way, we can calculate this. Now we have to consider the error of first output layer node in all three context windows. So we take the sum of all these errors at different context windows. But in this case, we can represent O11 as OC1 like that. So here, after calculation, we will get this outcome, because dE derivative of E with respect to summation part is already calculated here in this part, in the error calculation, and we represent this error as E. So here for first node we represent is E1. Now this is the second part. Second part is for C is equal to 1 to C. Now for second part it is calculation of derivation of UC1 with respect to W-11. So we will just take the weight measure for UC1 and UC1 is calculated here. U11 for UC1 it may be like W-11 and W-21, W-311. Actually we already discussed that in all three contexts we use due to the similarities in output values, same matrix will be used here. So we use this weighted matrix. So we just put this put the value of UC1 here and taken derivative of t with respect to W-11 which is equivalent to H1. So now after multiplying both we get these two values here. We can also say it like this W-C1 W-. Now we can apply traditional weight updating techniques that we generally used with all backpropagation related earlier tutorials also, that the new weight of the neurons will be equal to old weight of the neurons minus new. This is generally we call learning rate, and we generally put any value between 0 to 1 as a learning rate, but generally we put 0.5 like that for average learning rate, and this is the error we calculated here. So after that this is the updated weight of this neuron, or here in this matrix. Similarly we have to update all these weights in the matrix. We can generalize this calculation by considering total C context windows and vocabulary of size J as we did earlier. So in this case we can say that the error will be the W-Ij means weight of this matrix W-Ij instead of 1 1, that it can be calculated by taking the first to calculate that first we will take the derivative of error with respect to W-Ij, and we use this derivation result here to update the value of the node value of the neurons W-Ij. Now the next stage is to apply the back propagation from the hidden layer to input layer. Now till now we had applied the back propagation from output layer to hidden layer. Now we have to apply the back propagation from hidden layer to input layer. So first of all, actually the main aim of this back propagation is to update the weight of all these neurons in the in this matrix. For example, this is the W11, W12H1, W12 like that. So we have to update the weight of these neurons. For this, first of all we will take the gradient with respect to H1, because we are getting the summations at H1. So first of all we will take the gradient of E with respect to H1. So d gradient of E with respect to H1 can be calculated as J is equal to 1 to 5, because here we are getting the vocabulary Here our vocabulary size is 5. DE derivation, this will be the summation of j is equal to 1 to 5, and derivation of error with respect to UC1 into derivation of UC1 with respect to H1. So here the back propagations will be like that. Here UC1, here H1, so it will be like that, and after that we will apply this updated weight in this back propagation. So we already calculated these weights, these derivations, and this can be given here like that, and this part will be resulted in this derivation output. Now the next step is to update the weight of W11. We have to calculate another gradient with respect to E, another gradient of E with respect to W11, and it can be calculated by taking gradient of E with respect to W11, which is again a chain of H1 to W11. So this is the back chain from H1 to 11, so we can expand it through chain rule, like DE derivation of E with respect to H1 into derivation of H1 with respect to W11, and we already calculated this part here, so we will use this part here. And now the derivation of H1 with respect to W11 is very easy, because in earlier we already calculated H1 like that. So by taking the derivation with respect to W11, we will easily get X1. So this is the X1. Now by using this derivation, we can update the weight of neurons. So the new weight of neurons W11, this is our W11, also represented here, is old weight of W11 minus new, this is called learning rate, and derivation of E with respect to W11, which is calculated here. In equation 15. So similarly we can update the weight of W12, W13, W21 and till W53. So these are the weights that we can update. And we can repeat the same back propagation steps until we get some optimal or stable weights of all these neurons in this matrix and all these neurons in this matrix. Now we can generalize the weight calculation as we did earlier by considering total C context window and vocabulary size as J. The gradient with respect to HI can be calculated. J is equal to 1 to capital J. So here the only difference is that instead of J is equal to 5, we have taken, instead of using 5, we have taken J and UCI. Instead of using the first node, so our calculation result will be this. So these are the just simple derivations and can be calculated like this. Similarly, the gradient of E with respect to Wij can be calculated as by using the reverse chain rule that we discussed here. We have calculated the derivation of E with respect to H1 by using the reverse change from UC1 to H1, and now we will calculate the derivation of E with respect to W11 by using the reverse chain from H1 to W11. So we use this reverse chain related information in expanding this derivation. So derivation of E with respect to H1 into derivation of H1 with respect to W11. Now we can easily, so this is a capital J, this is a capital J and this is a capital C. So this is our calculation output, and after that we can update the weight by using the similar fashion that we did here. So we try to explain everything through a very simple toy example, and we can consider these references for further readings.